Okay, good morning, everyone. Yeah, it is my great pleasure to introduce this speaker, this series of seminars of the MAC. Allan is originally from Canada, with ancestors come from Scotland, as you can see, guess from the name, right? And he started his career path in Toronto, doing a PhD on relativistic density functional theory. I guess he didn't like it too much because he will continue along these lines. He got a position at the National Research Council in Ottawa, also in Canada. He didn't stay long there, apparently it was too cold, and he decided to move a little bit further south to Indiana University in Bloomington, where he was part of let's call it a dream team, together with Steve Girvin. They managed to put Bloomington, which is just a very small Midwest city in the middle of nowhere. They put the city on the map, at least on the physics map. And I was lucky to be part of it on my postdoc when I was way younger. Back then we used to live all the time in the lowest landau level. It sounds extremely boring if you think about it, but you can't imagine how much fun you can have there. I mean, you have all this, quantum Hall effect physics and all these things. Allan was a pioneer in this business. He moved to University of Texas at Austin, further south, to warmer places, where he is now, and I have to read it. He holds the C.W. Richardson Foundation Regents Chair in Physics. Very long title. He's also the director of the Center for Complex Quantum Systems, which may be something similar to what we have here, the IFIMAColloquium, to some extent. And well, Allan is actually part of the history of condensed matter physics, but most importantly, he's part of the present. And just to give you a glimpse of the things that he's doing, I'm gonna just read a few titles of the presentations that his students gave 2 weeks ago at the March meeting. Okay, just to give you an idea of what is that he is doing. Itinerant electron ferromagnetism in varied materials, an investigation of the magnetoelectric monopole response in chromium, electric field tunable hybridization in molybdenum diselenide bilayers, Exciton Condensates studies of semiconductor varied materials, pressure tuning of electronic and magnetic properties in a topological antiferromagnet, topological magnetoelectric effects in magnetic topological insulator thin films, and the list goes on and on for a while. So this is the kind of things that he's actively pursuing. The word moire appears quite a bit in the work he does. Probably you know that he was the one who told us that maybe if you rotate a monolayer graphene on top of another monolayer of graphene by a small angle, then you are going to have some fun there. And then our dear friend Paulo Jarillo somehow took over, and he did, the history, the rest of history, right? You know the story. I'm not gonna list the words that he has. He has them all, except one. Hopefully, next time around, he will have it when he comes back. And I have, as you can imagine, I have learned from him. I don't know how many things, a lot. Unfortunately, I think I have forgotten them all at this point, except for one.
Me too.
The only thing I actually remember is that once he told me, keep working and good things will happen. And well, he has kept working and good things keep happening to him. And I hope that being here is one of them. So Allan, whenever you're ready, it's
okay. Thank you. Thank you. I've had already had a wonderful few days here talking to people, learning many things. I think this Madrid and this campus is one of the centers in the world now for condensed matter physics, and it's always a pleasure to be here. So I chose to speak about one of the topics that I continue to be very interested in. I'm not going to. about exciton condensates through the years. And I'm not going to speak actually of the entire history of exciton condensates, only my history with exciton condensates. And so my history with exciton condensates, if I can get the slides to advance, they did a moment ago. Help. Escape. Okay, it did. It advanced a lot, in fact. Okay, got it. Thank you. Okay, so as Wanho mentioned, I spent a lot of my life working on phenomena of electrons in 2 dimensions in Landau levels. And this is actually my first paper related to exciton condensation. It was written together with Louis Bray, Louis and René Cote. Louis got as he was reminding me the other day, a NATO postdoctoral, NATO grant, collaboration grant. I don't think you can get those anymore, right? I don't think they exist anymore, unfortunately. And what we worked on was some phenomena connected to the quantum Hall effect, which occurred when you, instead of having a single quantum well, you have a pair of quantum wells, and they weren't understood at the time. And what was going on in these systems was really exciton condensation, and we didn't know it at the time. And but in retrospect, it clearly is. And so this is, as I said, a double quantum well in semiconductor quantum well, gallium arsenide quantum wells, and aluminum gallium arsenide barriers. You can make this barrier between the 2 quantum wells strong enough that the electrons don't tunnel, so good approximation from layer to layer. And whenever you have a good approximation in nature, you can make it a perfect approximation in theory. And so those of you who know something about the quantum Hall effect, you know that it has to do with energy gaps, usually energy gaps between Landau levels. But in this case, it was an energy gap when these Landau levels in the 2 layers were half filled. And this is one of the figures from the paper. And what it shows here is a plot of interlayer phase coherence. So this is the expectation value, the density matrix between layer 1 and layer 2. And so what happens in the system is that a gap emerges because of spontaneous phase coherence between the layers. That spontaneous phase coherence between the layers makes a effective allows the electrons to hop between layers, as I'll talk more about later. It makes an effective hybridization between layers, and that's what opens up a gap between Landau levels that were associated with these fractional quantum Hall effects. At the end of my talk, I hope you'll believe that interlayer phase coherence, and strictly speaking, spontaneous phase coherence between 2 different groups of electrons is actually the proper, or the real definition of what an exciton condensate is. So I'm going to get back there, but first let me go back to the very beginning of Bose condensates, Bose-Einstein condensates. This is a nice picture of Bose. Bose, when he wrote this famous letter to Einstein around 1920, thereabouts, a little earlier, I guess. He was a Bengali physicist working at the University of Calcutta. And as most of you know, he was working about on the quantum statistics of photons and how that explained black body radiation and so on. And so that was the beginning of Bose statistics, but Einstein, in his last contribution to statistical physics, took it one step further. I'm showing you here an equation. I'm actually teaching a statistical mechanics course right at the time, right at this very semester, yeah. So we derived this equation earlier this semester. I think most of you have at one time in your life. So what this formula says that if you have Bose particles that satisfy Bose statistics, basically levels can be occupied by any number of bosons. And you can calculate, and Einstein was the first person to do this calculation, how many bosons if I have a gas of bosons, so states for bosons labeled by momentum, and you can calculate how many bosons can have non-zero momentum. And that's what this equation is. And you can see here with the little check mark in Einstein's own hand that even Einstein had to make sure the factors of 2 were right and pi. And so the important thing about this equation, which Einstein recognized, is that this sum is finite. The density of electrons that you can fit into finite momentum states at any given temperature, if you have non-interacting bosons, is finite. And all of in the thermodynamic equilibrium state, all of the rest of the bosons go into the same quantum state, the zero momentum state. And that's really, has profound consequences. It means basically, since a finite fraction of all the particles in the system are in the same quantum state, it basically makes that quantum wave function something macroscopic. And so, we can say that all of the bosons have a wave function, and of course a quantum wave function has an arbitrary phase, but that's the broken symmetry of this system. And if I take the expectation value for annihilating electron, then with a finite probability, I'm just going to measure that wave function that the electrons are in. And okay. Now, what we're going to talk about in this lecture, and what is actually probably more important in all of the phenomenology of condensed matter physics, is not boson particle pairing, but electron pair pairing. In the case of superconductors, these operators here are electron annihilation operators. So there's an expectation value for creating or annihilating pairs of electrons. So the center of mass state of, if you look at a pair of electrons in a superconductor, then with finite probability, the center of mass state of that pair will be the same, and we'll have phase coherence. So this is what happens in. This is the starting point for superconductivity, and but we're not talking about electron pairs. We're actually talking about electron-hole pairs. Excitons are electron-hole pairs, and the more general point of view that I will, which is relevant to, the current activity in this area, is that these are just two different groups of electrons. And for what I'm going to be talking about, the two groups are distinguished by layer. So you can put one group of electrons in one layer in a two-dimensional material world, and another group of electrons in another layer. And but more generally here, this is just two labels. C is for conduction, V for valence, just because that's the common example that people had in mind, as I'll mention again in a moment. And so when you have a finite expectation value in an equilibrium quantum state for electron-hole pairs. This is the same as saying, this operator measures whether or not the coherence, phase coherence exists between these two different groups of electrons. So when that's non-zero, this is basically electron-hole pair condensation. You can distinguish different examples of electron-hole pair condensation. For example, you can think about just simple ferromagnetism as electron-hole pair condensation. Also density wave states of different types. Right. Now, what are the observable consequences of spontaneous phase coherence between two groups of electrons, or what are the observable consequences of Bose condensation? So sometime after Einstein's work, as most of you know, it was realized that Bose condensation is the explanation for superfluidity. Bose condensation of Cooper pairs is the explanation for superconductivity. And so I'm going to actually talk about super transport in the systems I'm going to talk about today. Okay, so let me step back to excitons. Excitons, as the word is normally used, is a excitation of a semiconductor or insulator, which you can couple to by shining light on a system, for example, to make electron-hole pairs. And when you do that, the attractive interaction between the electron and the hole makes a bound state. So you have a bound state, let's say in a semiconductor below the continuum of particle-hole transitions, and these bound state electrons act like bosons, and they can form, the idea is actually goes back to the 1960s, that excitons are all over the place in materials. We can make excitons by shining light on a material. If we have lots of exciton or lots of excitons, enough excitons, or low enough temperatures. I think this is, as far as I know, the first paper which stated this, that they should condense into finite fraction of all of the excitons should be in the same momentum state and should be superfluid. And so what does that mean, right? Actually, I gave a talk on this topic a few years ago at NYU, where the work was done, and I asked, is there any institutional memory of this paper? And they said no. So apparently this was the lead author, Brandt, and he went back to Germany a few years later and people forgot about it. So, okay. But in this paper, they say something, and I'm going to say later that this something that they said is wrong, and it's wrong in a way that you couldn't possibly imagine in 1960. They said since excitons are neutral, detecting condensation of excitons, even though we have this notion of superfluidity, how could we ever see, how could exciton condensation ever lead to any interesting electrical effect, because they're neutral particles. And here's another paper from the early days of exciton condensation. This is a well-known paper by Walter Cohn and David Sherrington. And of course, in those days, people were thinking always about bulk materials. And they pointed out in this paper that even if you had an exciton condensate in some bulk material, even for the excitons, they wouldn't be a superfluid. They're neutral, and they're not superfluids anyway. It turns out the reason, and this is for bulk materials, this is a correct statement. And the reason they're not superfluids is because it's inevitable I say, I'm going to say over and over again that exciton condensation is just spontaneous phase coherence between two groups of electrons. And in a real bulk material, we can divide the electrons into bands, say valence band, conduction band. But there's always going to be something in the material. For example, even in a perfect crystal, electron-electron interactions actually can move an electron from the valence band to the conduction band. So there are quantum processes which actually have a phase and therefore pin the phase of the condensate. It's not true that any longer that the condensate wave function can have any phase whatsoever, because there are always weak terms, in practice often disorder, which pin the phase, and turns out that means it's not a superconductor. Okay, and so the statement that excitons will not be superfluids is, I think, also wrong for reasons that couldn't be imagined in bulk materials. It's really just to foreshadow what I'm going to say. It's the really isolating different groups of electrons is possible because you can put them in different layers in this world of two-dimensional materials. And yeah. Okay, so I also want to distinguish, and I'm going to talk about both of these as an important distinction between two different types of quantum states that for which the word exciton condensation is used. I'm going to use the word equilibrium exciton condensation, by which I mean there is a time-independent phase between two groups of electrons. The phase of this amplitude is time-independent. It's an equilibrium expectation value. And there's another case, which is what I'm going to talk about in the end, which I think is related to a body of experiment that is just starting now. And that's an example of an equilibrium condensate where the lowest energy exciton state is not zero, it's finite. So that means when the lowest energy exciton state is finite, that means there are no excitons present in the real ground state of the system. But instead you form a state where the chemical potential of these excitations is non-zero, and but it's still a well-defined chemical potential. Okay, and if I go from energy to time, that means that the phase of the condensate has a time dependence, which the time dependence of the phase is really the chemical potential of the condensate. Okay, so I said at the beginning that I started working on exciton condensates with Luis before I knew that's what I was doing. But experiments on this mysterious quantum Hall effect in bilayer electron systems went on for the next 20 years or 25 years or so, still now. And it's those experiments on those mysterious quantum Hall states that really made it clear what was going on, that these were exciton condensate states. So I'm going to tell you say a few words about those experiments. Okay. So these are this is a cartoon version. It's actually from a little review that I wrote together with Jim Eisenstein a number of years ago. There's a much more complete review I recommend to you if you're interested in this topic, written by Jim more recently. And this is a cartoon of a two-layer system. These experiments were done in the quantum Hall regime. That means two-dimensional electron system with a strong magnetic field, Landau levels, as Wanho said, and low temperatures. And so these are this is a cartoon depiction of states in a Landau level in one layer and in the second layer. In a magnetic field, each Landau level has a finite number of states represented by this pixelization. And these what I'm calling now exciton condensate quantum Hall states occur when the filling of a Landau level is equal to 1. And so if I describe this bilayer Landau level by doing a particle hole transformation for one of the two layers, then the condition for the condensates to occur is that the number of electrons is equal to the number of holes. So there have been a large number of really beautiful experiments on these bilayer quantum Hall exciton condensate states. The two most important groups are Jim Eisenstein at Caltech and Klaus von Klutzing in Stuttgart. And I'll show you some of those experiments in a moment. But this is just one way of saying, why should you have an exciton condensate when you have two Landau levels and the total number of electrons equals the number of states in one of those two Landau levels. Here's another way, and maybe this is a little bit more rigorous. So if what these equations say is if I have a two-layer system, I can imagine making, for example, a variational many-body state where I take every electron and put it in a coherent linear combination of the two layers, right? So, and if I put all of the electrons into the same coherent linear combination of the two layers, then I have macroscopic phase coherence between the two layers. That's exactly the type of state that Luis calculated in the paper I showed you at the beginning. And so it turns out that if I take this bilayer system and take the limit that the layer separation goes to 0, then the interactions between the electrons then become independent of layer, just in the same way that interactions between electrons are independent of spin. And so in that limit, the many body states appear in spin multiplets. Okay. And so in that, if I use that analogy between layer and spin, then it turns out this state where every electron in the entire system is in the same two-layer state, the same layer pseudospin state, that's a fully spin polarized state. Okay. And so this state is a state with maximum spin, maximum pseudospin. And we actually know in the quantum Hall case, in the limit of layer independent interactions, that there's only one state in the Hilbert space, this one, which one multiplet, which exists in the many electron Hilbert space. So therefore, that means that state is an exact eigenstate of the Hamiltonian, and it turns out it's the lowest energy state. Okay, so we really know rather rigorously what I'm saying is that You know, if I use this analogy again between layer and spin, you can imagine that if I take electrons and insist that they all have the same two-layer state, then if I pull the layers apart, then the bilayer system's like a capacitor. And if I make all of the electrons in one layer or the other layer, then I'm charging up the capacitor. It costs Coulomb energy. So the system wants to have all of the particles in the same two-layer state, but it wants that two-layer state to be half in one layer, half in another layer. And in terms of Bloch sphere, this is like it's mapped to an XY magnet. So it has the order parameter is basically a phase, and that phase is the phase of the that's the interlayer phase. And if there's now it's not working again. What did I do? Escape again. Okay, so you probably may have to tell me again. Okay. Okay, so bilayer systems at this special Landau level filling factor have spontaneous interlayer phase coherence. And so that means there's a condensate of excitons. The processes where that pin the phase of that condensate can be made as weak as you like in this system. And so if you put all of the excitons into a finite momentum state instead of a zero momentum state, then you'll carry a current through the system. So this is exactly the way superconductivity works and superfluidity works. And so here is what I'm going to claim is a spectacular electrical effect that is a consequence of exciton condensation and couldn't have been imagined in 1960. But here's the bilayer. In the case of the quantum Hall effect, many of you know that there are, even though the bulk of the system is gapped, there always are on-gap states at the edge of the system. And that complicates some things, some experiments. And that's the reason why this particular experiment, I'm showing you data from Jim Eisenstein's group. There's very similar data from von Klutzing's group. But they go to the trouble of making these annulus of electrons in each layer, so-called Corbino geometry. And they apply a bias voltage and drive current across the gap region. So the edge states don't play any role. It's all to eliminate the role of the edge states. So the bulk is gapped. So if you take this bilayer system and you only make contact to the top layer, you will find that the resistance becomes the resistance goes like e to the gap over kT. The resistance goes to infinity as temperature goes to zero. In a Corbino experiment, the system looks like an insulator. Okay, so it's an insulator. I'm going to show you this data twice. First, I'm just going to describe it, and then I'm going to explain it and come back and show it to you again. But what is found experimentally is that if you connect, provide a path to go from the outside to the inside through an external circuit in the other layer, then the resistance becomes finite. And what's more, a current starts flowing through the circuit in the other layer. So what's going on there? One of the things that's going on is, this is just electron-electron interactions, symbolically, top layer density, bottom layer density, times some interaction. And if you have spontaneous coherence between layers, then you can make a combination of the top and bottom layer density which has a non-zero expectation value, doesn't fluctuate. And what's left is an effective hybridization between the layers. So this is the spontaneous interaction induced hopping between layers that you have in these bilayer exciton condensates. It's perfectly analogous to the pair creation terms in a superconductor, for example, in the mean field Hamiltonian. So this is a term in the mean field Hamiltonian. So as far as mean field, as far as the quasi-particles of the system are concerned, one consequence of having exciton condensation is that you can easily tunnel from layer to layer, and both the layers become as one. And so let me remind you of how a circuit works, where you have leads forcing current through a superconductor. So this is normal metal regions, superconducting regions, normal metal regions. There's a good, very close analogy between this and the exciton systems I'll come to. So superconductor is gapped. Our exciton condensates are gapped. In fact, they're gapped because of this interaction-induced coherence between the two layers. So a quasi-particle at low energies can't go through the superconductor, it's reflected. But because of the superconductor, an incoming electron can be scatter off the condensate of the superconductor and be reflected as a whole. That's what we call Andreev scattering. That scattering violates conservation of particle number. So the mean field Hamiltonian violates conservation of particle number. And of course, the collective physics must restore that. And so we know that every electron that is runs into the superconductor and is scattered off as a whole, then I launch a Cooper pair into the superconductor, and there's a supercurrent that carries the current through the superconductor with no dissipation. Okay, so so eventually in the bulk of the superconductor, the phase of the superconductor will have a spatial gradient. It's a finite momentum state. Basically, the Cooper pairs, when the superconductor is carrying current, are condensed into a finite momentum Cooper pair state. And so how does that work for bilayers? So this is, you can think about this as the Corbino, this is, I'm imagining going from left to right. I'm forgetting about edge dates. I'm going to be a turn in a few minutes to talking about the current frontier, which is cases without a magnetic field. And then then there are no edge dates to worry about. So I just transport from left to right. These are electrically isolated layers. There's a barrier between them, which is tall enough that actual electron tunneling from layer to layer is negligible. But if I develop spontaneous coherence between the layers, an exciton condensate, then the quasi-particle Hamiltonian, the quasi-particles will see a large amplitude or a large interaction for tunneling between the layers. So in the presence of a condensate, electron coming in the top can be scattered and go out the bottom. And every time that happens, this violates the fact that the real system conserves number for each layer independently if there's no tunneling at all. And so every time this happens, then the system has to launch an exciton. And just a perfect analogy with the superconducting case. And so that's what this experiment shows is going on. A bias voltage is applied to the top layer. Quasi-particles can't go through this annulus because there's a gap in this system. That's the quantum Hall effect gap that got Luis and I interested in this when we first started working on it. Because because an exciton current is now driven from the outside to the inside of the system, then that's a current of, let's say, electrons in the top and holes in the bottom. And so these currents, in order to conserve particle number, currents have to flow in the external circuit. And so that's what's manifested here. A current is driven in this layer, even though no electrical bias is applied to it. It's really spectacular. There's some deviation between these two currents at high bias voltages and higher temperatures, simply because the gap for true charge excitation is not infinite. And so you see that coming in. Okay, so so what I've told you so far, and see what time it is. My watch is dead. I have 20 minutes, right? Yeah. That's what we learned about quantum Hall effect in Exciton from, that's what we learned from the quantum Hall effect about Exciton condensates. In my life, especially because of its path starting from quantum Hall effect, many pieces of physics I actually learned from quantum Hall effect, because Landau levels are maybe silly, but they're simple actually. And so a lot of physics actually occurs in a very simple way in Landau levels. But we'd really, my dream is for this kind of phenomena to occur without needing a large magnetic field and without needing a refrigerator, occur at room temperature without a magnetic field. So, and now I think we have a chance to get there. So this has been, you might say, a obsession of mine for many, many years. How to get there. Here's one system where we, 2D materials. 2D materials are much better than quantum wells because they're really thin. You can get quite high carrier densities in the 2D materials, and they're very perfect. The most perfect one is graphene sheets. This is what we're imagining here. And so you can easily take 2 layers of graphene separated by an insulator that makes a nice opaque tunnel barrier. But still close enough that there are strong interactions between the layers. And in this paper a number of years ago, we proposed that if you populated one of these layers with a number of electrons in the conduction band and the other layer with the same number of holes in the valence band, then you might get spontaneous phase coherence between these 2 layers. And it might occur at very high temperatures, because if the doping is high, the basic energy scales of these systems are high. And in fact, there is recent experiments that show you do get spontaneous interlayer phase coherence in the system. At how high a temperature, I don't know. It turns out that, graphene, even if you dope it so that the blue layer here has states in the conduction band, and the red layer has states has occupied holes in the valence band. The other band's not far away, and that really complicates all of the many-body physics, and it's hard to be very confident about any quantitative predictions. So the second best 2D materials to graphene are the transition metal dichalcogenides. And a great thing about them is that they're not only, very good 2D materials, but they're a different type of 2D material. They're a semiconductor that has a spectrum with a gap between valence band and conduction band. And so we want spatially indirect excitons in this system. And there is, there's an argument that actually should be pretty reliable, because These systems are actually very simple. That the exciton condensation temperature scales with the maximum temperature for spontaneous phase coherence scales with the binding energy of a single electron and a single hole in this system, called here the EXB, the exciton binding energy. And we know for these 2D semiconductors that the exciton binding energies can be quite big. They vary quite a bit, but maybe they can be maybe as much as a half a volt. This prefactor here is not known with any constant, but 10% of is a fairly conservative number. So 10% of a half a volt is 50 MeV. That's bigger than room temperature. So that satisfies my criteria. And so these are typically, these systems are what do they call this? Type 2 band alignment. So the lowest energy states, the top of the valence band in one material is or the lowest conduction band states are, and the highest valence band states are in different materials. They all have finite energy gaps. These numbers aren't, even if you make hetero bilayers of these 2D materials, you have a finite energy gap. But now I'm going to tell you that doesn't matter. Okay, so there is a vision I'm now going to explain that you can make an electrical reservoir for excitons, and even spatially, electrical reservoir for spatially indirect excitons. And you can make the chemical potential of that reservoir for excitons whatever you like. It's tunable experimentally, and it can, in particular, it doesn't need to be zero. And so you can have these, what I was calling before, non-equilibrium condensates. So that's really what I have in mind here, and it matters for quite a few details. But here's a schematic of what I mean by that. So this is a typical, 2D material stack. In gray, we have insulating hexagonal boron nitride, few layer graphene layers that act like metals that provide the gates for this system, and some material that's in which we're going to put carriers in the conduction band, and some in which we're going to put another layer in which we're going to make holes in the valence band, a separate a degree of freedom. So here I've imagined that that the top gate and the bottom gate are at the same energy. That's not necessary at all, but it probably is advantageous. But the idea is I can make contact I can have an electron reservoir for each of these layers, and I can tune what that chemical potential is. And so let me explain it this way. So this is just the equation of equilibrium. That if in each layer, if the electrons communicate with the contact and not with the other layer, then in each layer is in equilibrium with an electrochemical potential. This is just electrostatic energy plus what I'll call a chemical potential plus a band minimum, when it's in equilibrium, is equal to the chemical potential of the contact. And similarly for the other layer. These chemical potentials are actually many-body things. It's the energy to add another electron, okay? And in principle, you have to do your best job you can to calculate that, or if you're trying to understand what you expect theoretically in advance of experiment. But here's a rough picture. So let's say I have some density of holes in one of the two layers, and I change the density of electrons, then how does the chemical potential of the electrons change? So if the density of electrons is smaller than the density of holes, that's the left side of this figure, then every time I add an electron, then it will find a hole to form an exciton with, because there's a binding energy that it can gain. And so when you add an electron here, what you're really doing is adding an exciton and removing a hole. And once the density of electrons exceeds the density of holes, what you're doing is you're just adding another electron. So something changes here, and there's a chemical potential discontinuity. That's what we expect, a chemical potential discontinuity when the electron density is equal to the hole density. So now you can think about this problem and forget for a moment, about these what we would call charge gaps, jumps in the electrochemical potential as a function of density. That means the energy to add a particle is different from the energy to remove a particle, which means there's a gap for charged excitations. So generally what's going on here, this is, so typical variables defined by gate voltages for a 2D material stack. You can use gates to control the total electron density, and also make a displacement field between the two layers so that there's a difference between the electron, or you can control the difference between the electron and hole density. And so in this plot, you can see that the top is a color plot with the scale on the right is the electrochemical potential of in the electron layer as a function of these gate voltages. And so it becomes big if you try to put a lot of charges in the system and make them mostly electron type. So there's a tendency, if this dashed line here is a contour, and there's a tendency for a contour with a given electrochemical potential. So the gate sets the electrochemical potential, tends to go with a downward sloping line in this type of plot for the dependence for the electron electrochemical potential, and equal hole electrochemical potential lines tend to be upward sloping lines. So these cross at some point. So all of that just says I have two control parameters, two gate voltages, a top gate and a bottom gate, and I can fix the electron density and the hole density with them. The precise values of this depend in a complicated way on interactions. But something special happens at neutrality when the electron holes densities are equal and you have these jumps in chemical potential. Here, each of these electrodes each of the electrodes doesn't actually exactly pin neither the electron density nor the hole density is pinned. And so this is the region, there will be an overlap between these flat regions. And in that region, what's going on is you're in charge gaps for both the electron layer and the hole layer. The contact cannot inject carriers into any band in either layer. But there is an exciton binding energy, and there's a window in gate voltage space, there's a window where you can make bound electron-hole pairs, even though you can't make free particles. And so this is a technical detail. This is from a paper from the Mock and Shan group at Cornell University, in which this was actually realized experimentally. I won't comment on how these contacts are made, but these are reservoirs for electrons and holes, and you can show experimentally that you can identify a region here, which is in the gap for introducing carriers into either band. But by measuring the ability to charge transfer from layer to layer, you can show that, in fact, you can electrically control the density of excitons in this system. So in this regime, it's actually the difference. What happens is the difference, the bias voltage, the difference between the contact, the chemical potential of the contact to one layer and the contact to the other layer actually is obviously electrical tunable, and it is the chemical potential of the excitons. So you can have a reservoir for excitons. If you have two reservoirs for excitons, you can have circuits. And this is actually looking very much like the Corbino geometry quantum Hall experiment I showed to you before. And there are no experiments yet, but I do expect these experiments to be done. And I expect to see electrical properties very much like those occur that have been measured in the quantum Hall system. And we'll see whether or not in the fullness of time, okay, I'm going to skip this, whether or not in the fullness of time we can get to room temperature. Okay, so here's my message. Exciton circuits are coming. I think there's going to be a lot of beautiful experiments on this kind of superfluid, 2D superfluid phenomena. I have the dream that this will actually be useful. Actually, there are, I have a patent. Okay. Is real interest in figuring out how to design the right combination of material to maybe get, safely enough, make this safely room temperature phenomena so that it's useful for something. Certainly you get very, nonlinear IV characteristics. That must be good for something. And I haven't talked at all about, the spin and valley degrees of freedom. Turns out these spatially indirect exciton condensates tend to be magnetic, so that might be interesting. And also there's a whole, another side of the story. I tried to explain, how you can make an electrical reservoir for excitons. In optical studies of these 2D materials, as Francesca is an expert on, a very prominent, feature that you see is connected with trions, bound states of 2 electrons in a hole. And there's also a possibility of finding a region, a small region in this gate voltage space, where you can make an electrical reservoir for trions and have a Fermi liquid of trions. And so that's something I hope might be interesting. And also you can have regions where you have trion, a many body system, which is a mixture of trions and excitons, all electrically controlled. And so there seems to be a lot of stuff that might potentially become possible if my experimental friends are sufficiently clever and making everything work. So, okay, thanks very much for your attention.
Thank you, Allan, for the inspiring talk. I understand that somebody has a question there.
Thanks, Allan. I want how the dipolar interaction in these bilayers will change the picture of condensation, where you can have droplets as like cold atoms now.
Yeah, so in these bilayer exciton condensates, you can think about it as a bunch of interacting dipoles. But the the dipoles are all aligned in the direction perpendicular to the 2D planes. So the interactions between the dipoles are always repulsive.
Yeah, no, I was thinking more stacking more layers, so to have the interaction between them in between.
Yeah, I know what you're referring to, but I haven't thought it through. But that's a good thing to think about. I think there are a lot of things to think about in this area, and I'm really pretty optimistic that it's going to become an active experimental area. So, yeah, so that's a good question to think about. I'll write it down.
So one quick question, probably so is there any experiment or theory where they are predicting also some kind of exciton condensates using a very strong intense laser? I would expect like nowadays these femtosecond lasers, you would be able to have enough intensity also to create this regime where you have these phases and enough holes and particles.
So yeah, in particular, for these spatially indirect excitons, so there's all kinds of literature. Close to what I've talked about is making steady state by exciting the system in one well or the other. If it's a type 2 band alignment, the electrons and holes will make their way to opposite layers and form these excitons, which probably condense, and you probably can see it in PL. It might be that at the present time maybe there's too much disorder to see it, but yeah. So those systems are all very interesting, and I know that there are some recent experiments with Moray systems which claim to see exciton superfluidity. But in any event, these are really ultimately dynamic steady states, and you'll never get the same degree of control as you potentially can get using electrical contacts. Normally in an electroluminescent device, you typically put on some big bias voltage, right? Much bigger than the band gap. And so that you need to do that to get the carriers in there, so here the trick is that any recombination process is really knocked down to practically zero, because the electrons and holes are in different layers separated by a large band gap insulator.
Allan, so you presented the very simplified picture of your calculation, but I wonder how quantitative it could be for a system like TMDs. I mean, the size of the interactions, the internal degrees of freedom spin valley. So are you dealing with all this complexity matching?
Yeah, if I talk about interacting electrons and holes, I think they're actually, when the density is low enough that the excitons don't overlap spatially, they're pretty simple, right? That's just weakly interacting bosons, and we can't calculate with 1% accuracy, or even maybe 5% accuracy, the energy of a bare exciton. We can't really calculate. It's a very difficult problem to really know how strongly excitons interact, and that influences how rapidly the exciton chemical potential changes with the density of exciton. But you can measure all those things. So for the qualitative things, I don't think, it matters. And for the quantitative things, you can measure them. In fact, I showed you the color plot I showed you is just mean field theory. And mean field theory works rather well. Its main failure is that as you start to go towards the, BCS limit, when of very high exciton densities, then there are screening effects that aren't contained in the mean field theory, and they are, and that's obvious comparing theory to experiment, that the size of this charge gap decreases much more rapidly with the exciton density than in the theory that we're able to do. I think that's the main thing. And then there's also, the question about what happens at so-called Mott transition when you go to high exciton density. It seems like there are various confident opinions in literature that are contradict each other, and usually that whether there's a phase transition, a Mott phase transition to a state that doesn't have spontaneous coherence, or it's not an exciton condensate. That's one picture. Another picture is, just the size of the gap just gets really small when you go to the BCS limit. I don't think we really know which one of those is true. One of the outgrowths of this is if we want to know the physics of interacting electron-hole systems, spatially separated electron-hole systems, I think we're going to be able to measure them all. So, yeah.
Okay, you say that for your excitons, you need somehow phase coherence between electron and hole pairs, and you have an insulating layer in both conductors. So which are the conditions or limitations for this insulating layer? How thick can it be, or what can I put in the middle in both conductors?
So just to be clear, spontaneous, the word spontaneous interlayer phase coherence is equivalent to the word not excitons, but exciton condensation. And there's a compromise in how thick you make the insulating HBN layers. You want the interaction between the layers to stay strong. And in some senses, at least, it goes down when the layers go further apart. But you want the layers to be far enough apart that the rate of changing the exciton number in the system by these correlated two-particle tunnel processes, where you simultaneously add an electron and a hole from the two electrical contacts, which then form a bounce. A complicated two-particle scattering process, depends on the contacts a lot. These systems, it's hard to make contacts, as you know, and so that process is weak, and you need to make the interlayer tunneling, or the leakage current between the layers, sort of small compared to that. But I think this is already done. You can do it.
Thank you for the talk. Are you thinking about the effect of disorder, especially when you think on this circuit with excitons? You have different kind of disorder in the two layers. Would this affect the current or?
So it will, disorder, if it's strong enough, can certainly prevent condensation of these excitons, can unbind the excitons if it's strong enough. The thermodynamic measurement that I showed you before, that shows that excitons are present, because you can move charge from layer to layer by creating and destroying excitons before you can actually, introduce charges into the layers. But it doesn't show that they're condensed. So, a disorder can rip the excitons apart, and then obviously they can't condense. But even if they're still condensed, it will create some potential landscape for the bosons, and that will work against condensation as well. Yeah.
So, more questions?
Thank you. Maybe I missed that, but you have made the point about the phase coherence and the current.
Yeah.
Can you make the point about quantization of circulation? Is that possible in these systems?
There will be vortices. If you made a hole in the condensate, there will be vortices. I'm not sure, and you don't have the convenient electromagnetic coupling to the order parameter that you do in superconductors. So that makes a difference in some of the ways in which quantized circulation enters. But yeah, I actually have thought and without really coming to a conclusion about what's a real clean physical measurement you could do that would be sensitive to the single valuedness of the exciton order parameter and really show that you have long range phase coherence. So these types of measurements I talked about are really can measure the the diffusion constant or whatever is the right word to call it. They can measure superfluidity, but they don't measure phase coherence. So maybe there is a way to do it. Yeah, good question. Thank you.
Any other question for Allan? I guess maybe if not, this is time to wrap it up and give Allan a break.
Okay.
Thank you, Allan.